All right, so we had part one, geocentric tides, where we steel manned the globe with the best explanation for the semi-diurnal and diurnal double tidal bulge theory. Now we're going to go ahead with the geocentric explanation with some math. First, by eliminating the heliocentric explanation with the same math. So, prerequisite: tidal forces are influenced by equilibrium forces, a balance between the gravitational pull and the centrifugal pull of the moon, right? There's a bulge, meaning there's one in the front and one in the back. The bulge near the moon causing the bulge, will be bigger, and the one in the back will be a little bit smaller. The one in the back is supposedly caused by the centrifugal force to balance out the gravitational force in the front. All right, keep that in mind. That'll be very important. And just so we can have a little visual here, say the tidal forces are gravitational on one side with the bigger bulge, and then centrifugal on the opposing side to balance it. It needs this equilibrium of forces to exist at all. All right, just going to keep that in mind. I just want to set the tone here. We're going to be sticking with the equilibrium theory of tides here, where the Earth and Moon orbital system and the gravity and Newton's law of gravitation, along with mass, is going to be the determining factor and forces. Now, keeping in mind that we're going to stay within this theory, these are some of the things that we're going to be working with, right? It assumes that the ocean responds instantaneously, that the ocean reaches equilibrium, and that it's all predictable and stable and super simplified, not complicated at all. Also, that Earth is a rigid body with a uniform depth and has no movement and doesn't rotate and has no one uniform ocean basin and no frictional effect. So again, we're going to assume an awful lot of crap. For the bulk of this video, we're going to be delving into the equilibrium tidal theory, which is the one that most people will tell you about when you ask them. And we're going to go into the math behind it, and we're going to use math to destroy it. All right, we're going to take a quick look at Robert Bennett's paper, The Geocentric Testimony of Our Tides. It is a banger. Right, so thanks to Robert Bennett, we have this wonderful paper. We will go through the math, the proposition, and the conclusion because we all agree. So he set out to solve the problem of why do high tides occur when the sun and the moon are at the both near and far side. Essentially, like, why do we have the double diurnal semi-bulge, and how does the sun and the moon both interact to cause that bulge as per the heliocentric model? And then he has the other issue to solve was why the moon was more than twice as important than the sun in determining local tidal ranges. Of course, in their model, it's 400 times bigger, but 400 times further away, so it should be having a proportionate exertion of gravitational force, you would think, right? So we go into his proposition here, and he has geostatics, right? He's trying to find, with math, the acceleration at points A and B, that would be over here, A, and over here, B, with respect to the center of Earth, which is O over here, due to the gravitational influence of the moon and the Earth, right over here, as shown in this figure. So this is the basis for the math that we're going to go through in the next slides here. Pretty much the radius of Earth be RE, right over here, this thing, and then the distance between the Earth and the moon be D. So we're going to use that later on. Mass of the Earth being ME, mass of the moon being MM. We're going to be using all of that later. So essentially, again, we have O and X, like I said before, radius of the Earth, radius of the moon, distance between the two, and we start doing some calculations. We have the acceleration at point B, opposite of the moon, right? So at point B over here is given by A of B would be, let's see, G of ME, so it's mass of the Earth over the radius of the Earth squared, plus GMM, which is the mass of the moon, the mass of the moon, over the distance between the Earth and the moon, and the radius of the moon squared, or the radius of the Earth squared, sorry. And then equals, to break it down, it goes G of M, the mass of the Earth over the radius of the Earth squared, equals the gravitational force of the mass of the moon over the distance between the Earth and the moon squared, times 1 plus 2 times the radius of Earth over the distance between the Earth and the moon. That's how you read that. And over here we have the acceleration of point A facing the moon is given by. So again, it's doing the same calculation on the other side, and we'll just buzz through that here. And we have this wonderful sort of conclusion. Let's see if we can't move me somewhere else. How about up here? Go. There we go. All right, that's good. So again, figuring these calculations out, he's doing, the acceleration at point A and the acceleration at point B. So again, the tidal lunar acceleration of each celestial body. And he does it by calculating it like this. So he has the A of A equals the gravitational force of the mass of the Earth over the radius of the Earth squared, plus gravitational force of the moon, or mass of the moon over the distance between the Earth and the moon, plus the radius of the Earth squared, which breaks down to gravitational force of the mass of the Earth over the radius of the Earth squared, plus the gravitational mass of the moon over the distance between the Earth and the moon squared, times 1 minus 2 times radius of the Earth over the distance between the Earth and the moon. And of course, we solve this for the A of O would be the gravitational force of the mass of the moon over the distance between the Earth and the moon squared. That would be this point over here, A of O, right? So we're doing A of O, A of B, and A of A. So this essentially is all how you're going to calculate all of these functions, right? So here is where it's a better opportunity to visualize where we broke it down, right? So acceleration of point A of A is this one over here, B of B is over here, right? And then A of point A. So this is just showing you in the diagram where we were calculating it. So continuing, we have the acceleration point A, B with respect to O, right? So again, A, B with respect to O versus B, right? So it goes O, or goes A, B, O, which would be roughly negative the gravitational force of the mass of the Earth over the radius between the Earth and over the radius of the Earth squared, 2 times the gravitational mass of the moon times the radius of the Earth over the distance between the moon and the Earth cubed, right? So that would give us roughly the same thing over here. It's almost the same formula, same calculation over here. And then we finally get to this page here when we finally calculated the combined effect of the moon and the sun when they act in a straight line. So this goes back to our constructive and destructive interference, along with tidal wave theory and fluid dynamics. When the waves go in the same direction, they constructively interfere, increasing each other's speed and size. When they perpendicularly intercede, they go slower, and they will slow each other down and bring each other to a smaller size, right? Super easy. And this is sort of the same effect. It's talking about when the sun and the moon are orbiting and they get close together, then that is a constructive interference, and they usually result in the spring or neap tides, right? But this is what it's talking about, is when it's combined, when the gravitational forces are combined in the straight line, this is what the expression of the force would be, right? So it says quantifies the acceleration difference due to the gravitational attraction of the Earth, moon, and sun, considering the order of magnitude of the radius of the Earth between the Earth and radius of the Earth between the moon, right? So it calculates the difference in acceleration from the near side to the far side. This is important. If we go back to our previous slide here, we can say the difference between, so right here, from A and B and to B and A, it goes from the near side to the far side. So as it travels from where we are to where it should be on the other side, how does it have an opposite impact on the bulge, right? Why does it increase the bulge then? So we would go through this again, replacing the moon with the sun to get the same calculations, assuming the gravitational forces would be the same. Perform the same calculation with the moon replaced by the sun. You substitute the mass of the moon, m, with the mass of the sun, ms, and the Earth-Moon distance, dd, with the Earth-Sun distance, dd. We're just going to swap some variables, do the same calculation. We get the combined gravitational effect when the moon and the sun act along the same line right over here. So over here, rather, this is where we have it. And then they have the acceleration difference across the Earth. So essentially, because the tidal forces are created by the difference in gravitational forces, not the actual force itself, then the difference would be the main determining factor. So we have the acceleration difference across Earth equals essentially the same calculation we had up there, adding those two together, right? So they calculate the acceleration difference from Earth's near side to the far side and to the gravitational attraction of the Earth, moon, and sun. So this would be the conclusion of Robert Bennett's paper. He determined the ratio for the lunar acceleration to the solar acceleration of the tides. So based on only the static forces of gravity above, then we can conclude that in these kind of units, we can calculate it out here. We finally get, including the supposed mass of the Earth and the moon. Again, mass of the moon based on optics, and 0.53 degrees being covariantly scaled for varying distances and diameters that all work as factorials. But if we convert it back to MKS units, we finally get the total ratio of lunar to solar tidal acceleration as 2.35. So I mean that the moon acts 2.35 times more than that of the sun, no matter where they are. This essentially would be that, the sun and the moon are each causing equal effects on the tides. Then you'd get diurnal equal semi-diurnal bulges and hula hooping all the way through. But you wouldn't get that if the moon was 2.35 times stronger than the sun. That wouldn't work, right? This also shows that tides vary by a factor of 2.7 times depending on the moon and the sun. Meaning, if the sun was over here, you might get 270% less tides as opposed to the moon being the main gravitational force. That's crazy. That's a crazy amount. Here we just have the math. We're going to, there's a summary tide here, just rounding it up. Those are the variables, the constants, the things we had before. And, of course, from the other values already determined of the lunar acceleration, we have the physics form at 2.16, NOAA 2.15, Hyperphysics 2.27, Wiki had it at 2.22, and essentially it was average at 2.27. So this was just a double check to make sure we were in the ballpark, and we absolutely were. It was absolutely on point. So, conclusions, right? The moon's acceleration of the tidal water is more than twice that of the sun of the new moon alignments. Now, remember, the new moon is when the moon is not there. It's its least luminous phase, and it's when it's next to the sun. So, it should be a constructive interference with the sun and the moon since they're both acting in the same way, right? It's not how it works, though. I mean, we definitely want to mention that the biggest determining factor in the tides is the phases of the moon, and more specifically, like the new moon phase. And it always affects the neap tides and the spring tides. It's always offset a little bit, so it's at a quarter or 3/4 whenever those happen, like clockwork. They oscillate back and forth, and it always is. It always coincides with the highest high tide. So the moon's phases is the biggest contributing factor, and it's almost like they'd have to come up with an explanation that would be ridiculous to incorporate when the moon is in new moon or not there, then it has a bigger gravitational effect or something. And oh, wouldn't you know it? That's their exact explanation. They say that when it's not there, it gains mass and has a bigger gravitational influence, and that's why we get the exact effect that we would get. Now, I'm going to say that's a score 1 for geocentric, but let's get back to it. And the geostatic prediction is consistent in our cosmic model where the Earth is stationary. Only gravitational forces produce the tides. What does that mean? Well, remember when they had to have centrifugal acceleration balancing out gravitational acceleration? Indeed, that's not even happening. The moon causes no centrifugal acceleration on the Earth tides because the Earth doesn't orbit the moon. Duh. Mathematically proven that there's no centrifugal acceleration needed in this math, just using the gravitational force of the moon and the proximity. Crazy, right? So the sun actually causes a centrifugal acceleration on the Earth in the consensus of the heliocentric model, or it would have to if it was orbiting the sun, right? Or if we were orbiting the sun, or if the sun was orbiting us, it would be a little bit different, right? So how the centrifugal force varies depending on the sun. I'm just going to use v as the relative, is the Earth's orbital speed around the sun, incorporating the average speed of 30 kilometers a second, and then adjusting for the ecliptical path for speeding and accelerating and slowing down, right? And we have some math to figure out for the centrifugal force. The sun would be on the far side, and then on the near side. So the far side, and this answer on the near side, and averaging in the center, we get about this much. So when we compare this, right, we essentially determine that because of the ratio of the centrifugal to gravitational acceleration of the sun is 11,764 times stronger. What the hell is that? The centrifugal force due to the sun's influence is 11,764 times greater than its gravitational acceleration. How in the world would that be? What? 1,200 times larger. If this was true, tides would be 1,000 times higher, and it would be absolutely insane. But what we just showed you is we already accounted for the correct tidal ranges using gravitational forces. So what can we conclude, right? Since gravity alone accounts for the observation of the double tides on opposite sides of the Earth with a different range of lunar and solar tides, right? So we only have the gravitational force that we calculated. Totally works out. 100% doesn't need centrifugal acceleration. That's a problem, right? So static gravity alone accounts for the double tides. Then the first conclusion is that centrifugal acceleration does not exist, either or it's zero. The second conclusion is that the Earth does not orbit we are stationary, in which case all of this math would make perfect sense. When the centrifugal acceleration of Earth's orbital speed is added to the gravitational acceleration, the heliocentric theory comes up as bullshit, people. Essentially nonsense. There is no evidence of centrifugal acceleration or force in the tidal behavior at all. So, again, concluding with Mr. Bennett here, we've concluded that this coincides with other geocentric tests performed, including Newton's bucket, Sagnet's rotor, Bennett's hiker, and Wang's linear Sagnac interferometer, all supporting an immobile, not fixed, stationary Earth. So conversely, there are no proofs by testing the scientific model or realistic interpretation of the test of the Earth orbiting the Sun. No centrifugal acceleration found, no supposed forces interacting, nothing of the sort. So the rise and the fall of the tides around the world and the toroidal breathing in and out is a semi-diurnal repetitive demonstration of Earth's central position in the world. Man, absolutely. Could not said it better myself. Thanks to Robert Bennett for his wonderful paper. All right, and to sort of help along Robert Bennett's conclusion, we're going to go into why centrifugal force matters in as far as the heliocentric model is concerned. It's part of the rotational dynamics, and it is the counterbalance to the gravitational influence of one side of the lunar bulge, right? The centrifugal force balancing the gravitational force from the moon is supposedly responsible for the off side of the lunar bulge side, right? It says that when two bodies, such as the Earth and the moon, are involved in a mutual orbit, each body exerts not only gravitational pull on each other, but experiences centrifugal force due to their rotation around a common mass. The tidal force on Earth due to the moon is a result of the differential of the effective gravitational force and the centrifugal force due to Earth orbital motion. The gravitational pull is stronger on the side nearer to the moon and weaker on the opposite side. Simultaneously, the centrifugal force is inversely outward axis of rotation through the barycenter, and it affects all parts of Earth uniformly. So essentially, this is required to balance to keep the tidal forces in check. If we don't have this, we don't have a tidal bulge from the moon at all, right? This is combined with the centrifugal force. This is required to get diurnal, mixed semidiurnal, and semidiurnal tides. There is no way to get it without it, right? It is essential for the balance of the forces in play. So this is another diagram. We're going to go from the F of C is the centrifugal force due to the Earth's rotation. F of G is the gravitational force. F of T is the resultant tide force. So again, there is no F of T without F of G and F of C, or there's no force of the tides without the centrifugal and gravitational force of the moon. So this is just a north-south cross-section through the Earth's center and the plane of the moon's hour. The dashed ellipse represent a profile through the spheroid composing the tidal force envelope, if you will, and the solid ellipse shows the result effect on Earth's water. So just going through the motions here, and again, one more time driving it home, just to be sure we know you can't have tides without a centrifugal force, which we just negated mathematically. The tide generating force is a requirement for the gravitational force exceeding the centrifugal force on one side, and the sideways forces is called the tractive force. So they have all these forces at play. If you take one away, the balance is blasted, and essentially you have no tide. So centripetal force and centrifugal force is the action to the Newton's third law for this orbit to have it going. So again, they're just going over how it's necessary, always been necessary. So again, here, gravitational forces from Earth, tidal bulges, giving you a net torque, right? Tidal forces from the Earth body raise tides on the moon. The rapid rotation of the moon offsets the tidal bulges from the Earth. So they're saying that each body exerts a force on the other, including gravitational and centrifugal. So it says as long as these tidal bulges are offset from the Earth's gravity causes a torque on the moon, slowing its rotation. So it's an off-center thing. And again, when the moon's rotation equals its orbital period, then the tidal bulges will continuously be aligned with the Earth-Moon line and the Earth's gravity, no longer producing the said torque. One more time, just to be sure we have all of the forces required, right? Needed to be F of C needs F of M and F of D. So the differential is what we're having to use, right? Let's see here. So it effectively balances the moon's gravitational pull It's crucial in distributing the tidal bulges symmetrically around the Earth. Without this, the water would be pulled significantly more towards the moon, leading to a different tidal configuration altogether. The centrifugal force ensures there is a bulge on both the side facing the moon and the opposite side. So, if you were to have no centrifugal force, the absence of this would necessitate a complete revision to the tidal prediction models and assume that centrifugal force and the moon's gravitational pull are in dynamic equilibrium. So, in conclusion, right, centrifugal force is not just a supplementary factor, but a prerequisite component in all the formation of Earth's tides, balancing the gravitational forces, right? It needs to be included in the tidal theory to explain the regulatory and symmetry of the tidal bulges that occur around the world. Proving its non-involvement would lead to significant changes in our understanding of tidal mechanisms. You don't say. You don't say at all. So, when the explanation of the two-bulge tide comes from the fact that the moon and the Earth form a two-body system, and the bulge of the water on the side that faces the moon is easily explained, but the bulge on the other side is due to inertia and harder to explain. So that's the force of the centrifugal, right? That's what it does. It's an inertial tendency resulting from the rotation of the Earth for objects to move away from both sides of the Earth, and the side facing the moon and the side facing away. So because the effect of things moving away from Earth is much greater on the side facing the moon, and that, of course, we're going over the centrifugal force is what we call it, but that's explain the forces of inertia. But according to this, there is a force that acts on all objects in circular motion, and that this is the actual equation that would be used. Let's see here. And this was just to compare the path of the sun and the moon relatively, so we could see their actual impact on the tides as they pass over. If the theory was that the sun and the moon pull the tides as they go by, we should be able to see that on these lines, right? Where this is the line where it actually passes by. We should see it over here. We should see it somewhere where the orbiting bodies of the sun and the moon pass by, right? We should see that. You guys agree? Well, let's take a look and see if we actually do see that. The more ridiculous aspects of heliocentrism, right? So here we have a nice image of the force vectors we're supposed to have right here for the differences in the gravitational force for the tidal force. And, this is just a nice animation showing how that would look on a globe with a orbiting body. Like, it would just pull all the water off every time. It's sort of like this, right? We'd have this kind of whipping giant tidal wave coming around and around and around, and that unified force vector would match the orbit of that celestial body. We don't have anything like that right now. If we tried to find a unified vector, they would not all point towards the moon. In fact, one of the assumptions of equilibrium theory is that all of the water is uniform and responds instantaneously to gravity, which is the only way they can get one of those force vector diagrams in the first place, right? So why would we think that we can actually have a unified vector for all the tide forces on Earth? Turns out that doesn't point to any celestial object, moon, sun, or otherwise. In here, this is the whiteboard that we have. So essentially, I did a whole bunch of map conversions in here. So we're going to look around. Here are the amphidromic points and tidal nodes, translated to all sorts of different projections. This is actually the depth map, how high things are on Earth. Of course, Antarctica is the highest land on Earth. Another map of the amphidromic points would be tidal nodes, right? Again, compare this to over here. This is exactly the same, but we have this map over here. This is a really nice HD map. Same thing over here. We can just use these in a minute for comparison, but this would be tidal amplitude, right? Tidal amplitude map, and a map. Actually, that's not even that. And here we go again for amplitude. And then this one as well. So we have all these maps chilling. We also have all the globular theories for how it works, right? Because we have all these videos, right, to show you how we think it works. Essentially, it's all nonsense. I mean, you'd think you'd be able to find it, right? You think you'd see the the way that it aligns. Let's see. Let's do the regular day and time, a day and night time and date.com map. Again, I'm not seeing a unified vector that pulls any of these tidal amplitudes around or in any way whatsoever, right? It doesn't even make sense that it would be pulling along the... It doesn't even make any sense at all. Let's see here. How about this one? Yeah. Yeah, there's no way that the sun or the moon has a unified vector of force that pulls all of those. It's not happening. I don't see it. I don't see it. How about this one? Same one. How about this one? Let's see. Looks like a little bit longer anyway. There we go. Here we go. Now we're talking. Let's get rid of me and take a look. Right here's the best animation, I think, of the tides that we can get. It's got all the amphidromic points, and it's got them rotating around 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think that's all there is, right? So, and again, the only correlation that I can find on all these maps would be exactly this, right? So we have my phone app displaying just the sun and the moon going around their track year to year. So what I have is a couple of different images trying to overlay. That didn't work. That was just the tide, regular one. There was this one, magnetic field. We can overlay that. Take a look at it. That works pretty well. We also have this one. Amphidromic points again, definitely works. But the best one by far is this one. And again, we just had this one up. So remember, this is what we're looking at, and look at the alignment here. Hits almost every single one of these, almost, except for this one. But that one's a little bit weird. Anyway, so that's how the amphidromic points tie into the geocentric position, is that the sun and the moon hit all of those spots. And even though we're not arguing that the mass and gravity is what's moving the water, if there is an electromagnetic interaction or a pull or some sort of proximity interaction, which there definitely seems to be, especially when the sun and the moon get together, especially when the sun and the moon get together and the moon is in new moon phase, like all solar eclipses, for instance. But that's what we have so far. And then we're going to go into another theory that I think No Fanfare had premiered the same day I did my presentation. So we're going to incorporate that. And just quickly going through all the maps we had made down here. So this one is pretty much the biggest one, or the best one. This is the actual tidal amplitude going around, watching the amphidromic points pushing and oscillating around. This one right here, right? So the clock up here, every hour it'll update. That's the real time. And then you can see how it actually oscillates around. And of course, I had it converted to AE just, for fun. Makes a lot more sense this way. And again, that ties up with the path of the sun and the moon. Now, if you're looking at it, every single point is on path with the moon. Isn't that crazy? Point, 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 point. The sun and the moon hit every amphidramic point on the tropics. Isn't that weird? And again, same thing here. You can see the hot zones. Same thing there. This is just the magnetic field line. Yep, this is the magnetic field present day mapped out. That definitely has an effect. Actually, we have to go back to the quadrupole version to see the absolute lining up of that. And then again, infodromic points. I might have made a couple. So this one is the M2 moontide. There are many constituents within the tidal harmonics, but M2 is the main one. It's the moontide. That one you'll see all the time. I think like 7 of the constituents make up 80% of all tides, but none. Amplitude, infodromic points on a Mercator, definitely a good map of tidal amplitude. So that would mean that this is where it gets high, this is where it gets low. This is where you don't see any, this is where you see a ton, right? This is supposed to be showing the fractal, right? M2 tidal constituent again. So that's again the main bulk of the tide. M2 again, down by the depth, longitude, another map, good old globe maps, put them on every single map I could find just to see what it would look like. Oh. Hey. And ocean currents makes way more sense. Look at how that works. Circle, 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 circle. Circle, 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 circle. Makes way more sense. I mean, honestly, of course it does. That doesn't, I mean, honestly, so all the currents, the hot, cold currents creating, the up and down, the back and forth, the equilibrium. And again, another way to look at it here. This is actually pretty great. Right. So the Gulf Stream mixing with the cold and the warm again. So it's doing the wind versus the ocean currents. You could definitely see some correlation there. It all plays into the tides, honestly. It's all part of it. And just wrap it up here with the math. We had, of course, the force for newtons for determining how to get the gravitational influence of each celestial body with regards to the moon and the sun. And of course, we had determined based on the distance and the heliocentric model. Again, we used gravity, we used mass, we used all the stuff that we've already debunked a billion times. I know we've used mass. We're not going to worry about that, okay? It doesn't matter. It doesn't matter because we're just going to debunk it within their model and then within our model. So again, gravitational force in regard to the tide was just the F of G equals the G over the M1 of M2 over R squared, just basic Newton's form of gravitation, which we can reduce again, but which we won't. Then you have the centrifugal force, which is just mass times velocity squared over the radius, which is the distance from the object to the center of rotation. Gravitational force with the tide, that was the same thing we had before, except it was times 2 and then big R, which would be the radius of Earth, over the radius or the distance between the centers of the two objects cubed. And that would give the gravitational force generating the tide. And we had the net force generating the tide, where we had to calculate based on this, the centrifugal or the gravitational minus the centrifugal, which is why if it doesn't exist, it's kind of a problem. And then back to Kepler's law of equal area, which was, of course, to get the area swept out by an object and the ellipsoid. So when we're dealing with an ellipse and the area under an ellipse, we do this formula. And this is, of course, from Kepler when you're assuming that the sun is in elliptical orbit. All right, so that's pretty much it for the summary. Let's go back. So ignoring the clock hands and the text and everything else, let's go through every layer. So we have the regular map, we have the ocean map, we have the heat map, we have the magnetic flux map, we have the node map for the amphidromic points, We have the M2 tidal constituent map. We have the magnetic declination map. We have the amphidromic point map. We have the tidal amplitude map. We have the second magnetic declination map. Yeah, but now we can do sort of layers, because I think heat and nodes is interesting. Heat and current, no. I think heat and ocean currents was cool. Yep, that works. And then also magnetic deck. So there you go. Right there, people, is the whole thing. Magnetic declination, magnetic flux, and heat is yeah, that's pretty much everything, right? That's how it works. Let's see. Let's get rid of this one. Do just this one then. Amphidromic system, ocean, and that one. Yeah. So all the overlays that we have, I mean, it's definitely magnetic. So we got to do two magnetic decks. Look at that. Magnetic decks, magnetic flux. That's a pretty good fit. Yeah, absolutely. So, I mean, the sun is definitely magnetic, right? And sun and moon are definitely magnetic. So there you go. And I know we were dealing with mass and gravity and things we don't believe in, and the math for gravity doesn't matter because we were dealing with, again, equilibrium theory of tides, which one of the assumptions was, in case we forgot, right? All oceans respond instantaneously to gravitational forces of the moon and the sun. The ocean reaches equilibrium with tidal forces all the time, resulting in a predictable and stable tidal pattern. It also assumes complex interactions and considers the Earth a rigid body with uniform depth and neglects everything like rotation, ocean motion, and friction effects. Again, it assumes an awful lot. It's essentially nonsense. We're just going to refute it within their model, all right? So while we will be dealing with mass and gravity and Newton's gravitational Newton's universal law of gravitation and a whole bunch of other heliocentric stuff, it doesn't matter. This whole assumption is stupid, right? It's assuming a bunch of nonsense. So the only way it gets a unified vector in the first place is if it assumes a bunch of bullshit. We're going to let them assume bullshit. We're going to beat them with the same bullshit. Then we're going to back out and beat them with logic and reason too. All right? Hang in there. So after all that math and all that nonsense pseudoscience from heliocentrism, what actually causes tides? What do we think? Well, I mean, what I think causes the tides, combination of this inward and outward breathing of Earth, so the general seeking of equilibrium that you get when you have giant oceans and whirlpools and tunnels, and also the general moving of the water back and forth, I think would be probably due to something to do with the moon. Absolutely the moon. The moon is the best thing that coincides. If you watch the periodicity of the phase of the moon, it always coincides with the neap tides, the spring tide, which is the highest high and the lowest low. And that's always when it's perpendicular to the sun. So right when it's about to catch it. And then right when it gets to the sun, of course, it can't actually approach the greater light as a lesser light while remaining luminous. So it, of course, loses its luminosity like a turned off light bulb. And when it gets close, that's when apparently it has the biggest gravitational effects. It multiplies its mass by not being there. And then that has the biggest effect on all the tides. It is the moon, most likely in the proximity. Right here on the top left is the in sync to where the phasing is. So it's in the speed that the moon is going across the map. In the full moon and the new moon wouldn't be the maximum and minimum. It's actually shifted 45 degrees from there. But aside from that, what we do know is that there are amphidromic points all over Earth, right? These little places of zero amplitude that control or seem to control tidal amplitude, or where they sort of fluctuate and they oscillate the tides around them. And then we can draw things like cotidal lines, and we can take a look at like one every hour. Where would that cotidal line of that basin be? And we get a rough idea of the general flow of a tide over a course of a day. But we don't know what they are. We don't know what's underneath them. The heliocentric explanation is that they're just a bunch of different formed basins on the bottom of the ocean. You know, they're just kind of like this. What's this? Yeah, so they're just, regular basins. No. This is just something that they use to explain within tidal dynamics, where you can have an oscillation, and this is what the co-tidal line would be every hour around the main center. So one of these centers would be a place of no tidal amplitude, so no fluctuation from high to low, and then around that would oscillate the highest high and the lowest low for the region, right? And we have a couple of different diagrams. I think here's another one. Right, it's a nice apodromic system. That's exactly what they're talking about. But then they just say, "Oh, that's just pretty basins that all happen to form perfect amphidromic bottoms." They don't really know what the bottom of that all looks like, right? But I'm saying that there's something else going on there. There could be something like a whirlpool or a giant, ebb and a flow of the waters in and out from somewhere on Earth, where they're coming in and going out. Not sure, but there's definitely an ebb and a flow, and it would coincide with the moon. And beyond that, you have the highest high and the lowest low, which is when you get constructive interference and destructive interference with the fluid dynamics within waves, right? If they're going the same way, they get bigger. They're going into each other, they get smaller. Super easy. And then you have essentially the two tides would be, well, actually, we should go into that. They only have one tide, but it's the M2 tide is the biggest tide, the lunar tide. But they have many, many other tides. When we get in, I guess the next video we'll get into tidal harmonics, how they actually predict tides. Honestly, we're not going to go into this too much because this is going to be a whole thing by itself. But how they actually predict tides and how it actually works is they do historical hydrodynamics, and they look at the frequency. They break it down into harmonic constituents, and they say, essentially, right? So they have amplitude, frequency, and phase. And between those two things, they can find everything that they need, right? So they divide the tides usually into things like M2, S2, N2, K1, O1. There's usually, so that larger lunar, smaller solar. They'll name the front bulge and back bulge different M4s for the first override of M2 constituent. But essentially, like they're all the same. So let me look at couple of ways to predict just real quick. We'll give a little preview for what we're looking at next time. Anyway, that's how it really works.